Welcome to the DESI ASTRO. In this Python tutorial on SciPy, our objective is to learn about orthogonal distance regression, also called ODR. So, basically, a regression means that you have a set of data points and you want to fit a model through these data points to get a continuous model. Okay, so you must have learned about ordinary least square fitting or regression. So in which like you have error only in your dependent variable. Say suppose you have a curve y equal to mx plus c. So your error is only in your y data. Okay. So unlike your least square regression, ODR is useful when you have error or uncertainty in your dependent and independent variable both. I mean in your x and y both. Okay. And the main difference between ODR compared to your least square regression is that it computes error. I mean it's calculate error okay, in the perpendicular direction to the fitted line, not just vertically. So here you can see that I have a ODR fit. Okay, so here you can see that I have error in both x and y, and the red one is my fitted line. So what it does, so here you can see that the green line is line perpendicular to the fitted line to the data points, and the yellow line is just vertical to the line. So what the ODR does, ODR computes error perpendicular to the the fitted line, not just vertically. So this is the main difference, right? So what we have to do, I have to like reproduce this fitting, like we have this xy data points, error in xy, and then I have to find its slope and its intercept, and also the error in their fitted parameters. So you can fit any profile with your data points, Gaussian, exponential, whatever you want, but for time being I will be doing only the linear one. Okay, so let's do it. Let's do with the Python coding. So for that I will be importing some necessary library to do my stuff. Okay, so I will import some library like NumPy, Matplotlib, SciPy, and random module. So let's do it. So let me import libraries. So I will import NumPy as NP. So this take your number, a numerical Python, right? Then I can import Matplotlib. So import Matplotlib dot pyplot as PLT. So this will take care of your data plotting and visualization. Then I can import random module. So import random, and then I can import this SciPy ODR. Okay, so from SciPy dot ODR import ODR, and then you can also import model to fit, and then you can also import the real data. Okay, so now our step 1 is done. Then I will define my linear model. Okay, so in my case I have to like do a linear, so y equal to mx plus c. So you can define, so for type here function def, so definition, and you can give here say linear model as your function, and you can give your parameter as a b. Okay, so x and So basically your like B is your like vector, okay? So B acts as a vector. So B acts as a vector of slope and intercept, right? Then I can return the model. So return. So I can return. You can return as a b0. Okay, so it's slope into x, and then plus your intercept is b1, right? So our model has been created. Now we'll be getting this model object. Okay, so you can type here model equal to model, and then you can give here this function linear model, right? So linear model. Now our next step is to generate data points x and y. So I can generate data points x I can give as np dot linear space, right? And I can go from say 0 to 10, and I want to give say 20 data points, right? Just keep it simple, only 10 data points. And then similarly you can define y equal to your x data. Okay, so define here y equal to x plus noise. Okay, noise. So y equal to, you can give some value here. Say I can give value here 2.5 like that, and then you need to add your noise. Okay, so for noise we will be using a random data sets, right? So plus np dot random dot rand int. Okay, and then you can add some random integers from 1 to 10 and in the size of your x data. Okay, can make a size or length. So size equal to x data, right? So here you got it, right? Your y and x, right? Okay, so now you can, okay, so this much you have done. You can also plot it, okay, for time being. So plt dot scatter, okay, x comma y. So here you can see that here you have a data points, okay, and you have to fit a regression ODR regression through that. Okay, now we will define our error in both x and y. Okay, so you can define x error. So x error equal to, you can define here np dot random error, random dot rand int, and then you can go from, say I want to go from 1 to 3, and then size of same size as x dot size. Okay, and then similar stuff you can do with y error also. So y error equal to, just to do the same stuff, or maybe you can change a little bit. Okay, so yeah, maybe you can put it 4. Yeah, 4. Okay, now okay, so now plot this data. Okay, so I will just comment it. Okay, and then I will plot my data. Okay, so create a real data object with this. So you can do here data equal to real data, right? So real data, see what it takes. So it takes your x, y, and xx and xy. So see what is parameters are. So if you check here, so So xy is array, and these are the xs and sy is your error, okay, array. So let's put it. So you can put here xy, then here you can give here sx equal to x error and sy equal to y error, right? So now we have created the real data object. Now okay, so now we have done this much. Now we'll create a ODR object with here initial guess parameters. Okay, so I mean it is like initial fit to the data points. So for type here ODR equal to ODR, right? And then you can give your data, okay, real data. Then you want to fit your model, right? Then see what it takes. So it takes okay, so it takes your data model and beta 0. Okay, so here beta 0 is like your initial parameters of the guess parameters. Okay, so you can give here beta 0 equal to, you can give say 1 1. Okay, so you can type here beta 0 is initial guess to slope and intercept parameters. Okay, parameters, right? What is the mistake? Index. Okay, there should be comma, not dot. Now fine. Okay, now we'll run this deviation, right? So you can give here output, okay, output equal to ODR dot run, okay, and you can give the function, so it will run the ODR. DOR, oh, there should be ODR, right? So and now then you can like extract your parameters. So you can extract slope and then slope and intercept. Okay, slope and intercept parameters equal to, you can extract as a output dot beta. Okay, so you can put here output, so output, so here's the object, right? And then you can find here a slope and intercept, right? So here's the value of slope and intercept, right? So let's go further and plot this data with the error bar. So for that, type here prt dot error bar, right? You can give your x data, y data, your x error, then you can give here y error, right? And after then you can give your formatting fmt, right? You can give some you can give the e color of the your error bar equal to red, and you can give say, you can also give say cap or leave it. Okay, now run it. What is the mistake? X error is not defined. Okay, so x error equal to, you can give x error, and then y error equal to, you can give y error, right? Now what is the mistake? There should be y error. There should be a y error. Okay, now fine. Alright, so we have plotted these our data points with error bars, right? You can also give cap size to this, right? So type here cap size, you can give 2.5. okay, so you can see you got here cap size. Maybe give it more, 6.0. okay, so this is a error bar, the red one, and blue one is your data point. So you can give a label, so label equal to data points, right? And you can type here legend, plt.legend, and then you can type here plt.show, right? So here you got your error bar with the data points. Now I will plot this fitted lines with our parameter slope and intercept. So type here plt.plot, plt.plot. You have x data, okay? You have x data, and then you can do your y fit, or just so you can type here y fit equal to a variable y fit equal to x, or just okay, so slope into x plus okay intercept, right? So you can give here y fit, and you can give a level equal to ODR fit, right? So here, and you can give the line width for line width equal to 5, and color you can give black. Okay, so here is my data points and it is a line, okay? You can also make your that's fine. Okay, so here is my regression. So you have blue one is the data points, red one is the error bar in x and y, and this line is your ODR fit, okay, to these data points. Okay, you can also like get the parameters printed. So output dot pp print function. Okay, so here you can see that you have this beta parameters, slope and intercept. Okay, so you have this standard error, and there is a covariance matrix, so which correlates with the relations between your parameters, slope and intercept. So like how much they are correlated, right? You have residuals and inverse conditions. So this is the summary of my ODR fit, okay? And so you can also give a title if you want. So plt.title, and you can give title as a so you can give title as a SciPy ODR fit, okay? So our job is done. So here is my final ODR fit, the data points and error bar, right? So if you run this code again and again, so like it will change. Okay, right, it will change the parameters also. You can see slope is this much, so if you run it again, it will change a little bit because our random errors are changing. Okay, so this is how SciPy ODR is done with error in your dependent and independent variable x and y. So let's review the code once again. So I have explained about this ODR regression, that it calculates error from the perpendicular to the fitted line, not just vertically like ordinary list or square fitting. And then I have implemented libraries, NumPy's SciPy random module, and then I have defined a linear model. I have created that model. I have defined your x and y data. So y data has some noise or a scatter. Then I have defined your x and y error. I have created the real data with these data sets. I have like run this regression. I have found out its slope intercept, right? Then I have plotted the error bar, and finally I have defined y equal to m plus c your line, and then I have fitted a regression. This is my final product in form of visualization, and here is my full result. So thank you, and stay tuned for the next video.